talk, I want to take an opportunity to advertise the next COMET Plus webinar, which is on the 10th of January, and this will be given by Alexis Heresiewicz, who will be talking about using INSAR for measuring peatland surface motion. Today's speaker is Ben Esse, who is a postdoc at Manchester University. Ben combines satellite measurements of SO2 with global meteorological models to measure volcanic gas emissions. He has looked at a number of volcanoes, including in Iceland, St. Vincent and La Palma, and he's also working towards automating his analysis to provide an ongoing database of degassing volcanoes across the globe. He will talk about this in his talk today, which is titled From Measurements to Processes, What Volcanic Gas Emissions Can Tell Us About Volcanic Eruptions. The talk is going to last for around 35 to 40 minutes, following which there'll be an opportunity to ask Ben questions. So if you have any questions, please put them in the Q&A. Over to you, Ben.
Cool. Thank you very much. Thank you, everyone, for coming. Yeah, as Isabel said, my name is Ben, and I am a postdoc in Manchester, and I'm primarily interested in looking at what we can use satellite SO2 measurements to tell us about what volcanoes are doing. So we'll go through a few examples of some of these eruptions that we've been looking at recently, and hopefully by the end of the talk you'll agree with me that these satellite measurements are really useful for understanding volcanic processes. So but let's start by saying thank you to a big list of people. I'm sure I will have missed someone off here as well, so apologies if I have. But this has really been, we've been looking at these volcanoes from across the globe. So there's been people in St. Vincent, people in La Palma, and people up in Iceland, as well as other collaborators beyond that that have really helped us piece these bits of puzzle together. So without any further ado, so the key points I'd like to sort of get across by the end of this talk is the fact that we are able to use sort of daily satellite SO2 imagery to give us sub-daily 24-hour SO2 emission rates from volcanoes, and that we're able to do this in near real time. So this provides a really key monitoring source for volcanic activity around the globe, especially for volcanoes that are more either more dangerous and you can't get up close and personal with, or that are more remote, so that are hard to monitor from the ground and all the time. So we're going to look at 3 eruptions in particular. These from 2021. So the eruption of La Soufrière in St. Vincent, which was this a really explosive eruption. The eruption of Fagradalsfjall in Iceland, which was a more sort of low-level effusive eruption, and the eruption of Tacogate in La Palma, which was kind of a bit of both. And I apologize for any of my pronunciation on any of these. It's 3 different languages, and I'm struggling to keep up with them all. And the key point that I want to try and get across in this is that we are able to infer information about the magmatic processes driving these eruptions purely from looking at the degassing data. And this is kind of data that has been relatively untapped until recently. And I think it's really in recent years and recent advances in sort of sensing and analysis techniques have allowed us to get much deeper than previously. So I guess why are you interested in volcanic degassing at all? So volcanoes are this major source of various gases and aerosols into the atmosphere, including many quite volatile species. So and understanding the emission rate, so how much of these gases are coming out, and also the composition, so what gases are coming out, is very key for monitoring and forecasting volcanic activity, because changes in the gas, the magnitude of gas emissions or the composition is linked to changes in the magmatic system. So that it really helps with understanding the magmatic processes as well. But also on the flip side, once these gases are emitted into the atmosphere, they can impact both local and global air quality and climate. So for both health and sort of global climate purposes, it's really key that we know the flux of these gases coming into the atmosphere so that we can best mitigate these. And there are various ways that we can measure these. We can do these from the ground, either sort of actually going into the plume themselves and measuring samples, or from afar using remote sensing. We do the same with drones or helicopters or even aircraft, or we can look at with satellites from space. And so this talk is going to be focusing on space-based measurements of SO2. So this little gas here. Now there are various satellites that can measure volcanic gases from space. I'm going to be using results purely from TROPOLI, which is the tropospheric monitoring instrument. This is an ESA instrument on board the Sentinel-5P satellite that was launched in 2018. And this provides us daily global coverage using this sort of polar orbit by wrapping itself around the globe like this. So we get about 14 orbits a day that give us a global coverage. And this drop only can give us information on various different gases, so nitrogen dioxide, ozone, methane, other ones, etc. The one that we're interested here, obviously for volcanic purposes, is SO2. Now, why SO2? Why not any other gas? It's because SO2 is the third most abundant volcanic gas after water and CO2. But unlike water and CO2, there's barely any of it in the atmosphere. So we're actually able to, it's very easy to detect over basically a zero background, whereas water and CO2 are quite difficult to measure the small increase over what's already in the atmosphere. And the really key thing about tropomi over previous instruments that we had available is the really, I forget if it's high or low spatial resolution, very good spatial resolution of 3.5 by 5.5 kilometers. Now this might sound quite large compared to like visual imagery, but for gas remote sensing, it's really quite good. And this means that we're actually able to drill down not just gas that's high up in the atmosphere, it's easier to measure, but we're able to look very, very deep into the atmosphere, into the troposphere and almost down to the surface. And to sort of give you a comparison about over previous missions, before tropomi, the best we had in UV anyway was called the ozone monitoring instrument. You can see they're quite creative with their names. This is showing an example from one of the eruptions that I'll be presenting later on from La Soufrière, using this sort of SO2 plume. And you can see when comparing OMI with the updated tropomi, you can see that jump in spatial resolution. It's providing much more detail within the plumes themselves, so we can pick out more of what's actually going on there. But also because each pixel is effectively averaging over a smaller area, this produces much higher sensitivity, and that's what allows us to look further down into the atmosphere. But this imagery alone isn't everything we need. So we get basically a single picture of the globe in terms of SO2 every day. But there's vital information that's missing. We don't know, firstly, what altitude the gas is at, and that's very important. I'll move on to a little bit more of that on the next slide. But also, we don't know, well, if that gas came from a volcano, or what volcano it came from, and when and at what altitude it was emitted into the atmosphere. And all these are very important for underpinning the final emission rates, which is what we really want to get at in terms of the volcanic activity. So why is the altitude of the gas so important? If we sort of consider, if we've got a single pixel here, a little plume, a little puff of SO2 that's in our atmosphere, and we're going from the ground at the bottom all the way up to space at the top. What we're really interested in is what's called the vertical column density. And this is it's basically if you draw a line from the surface all the way to space, how many molecules you'll encounter on your way out. And this is what we really need when we're measuring how much gas is in a plume. But this isn't what tropomi measures. Tropomi, when it comes along its orbit, it actually measures what's called a slant column density. So it's looking at an angle through the atmosphere. It's not always looking directly down. Sometimes it is, but out to the side it won't be. So this is what's called slant column density. And the two of these are convertible using what's called an air mass factor, or AMF. So we take our slant column density, divide it by our AMF. This gives us our vertical column density. This AMF value depends on several things. It depends on the atmospheric properties, view and geometry, but also on the SO2 profile, so where the SO2 is in the atmosphere. So you'll use a different AMF depending if you've got a gas low in the atmosphere or high in the atmosphere. Now, we don't know this at the time of measurement, right? You could have a passive plume that's at, say, 2 kilometers into the air, or you could have an explosive plume that's 15 kilometers into the air. Now, tropomi as a sensor doesn't know that, so it automatically calculates 3 box profiles, one at 0 to 1 kilometers, so from the ground up to 1 kilometer, one at 7 kilometers, and one at 15 kilometers. And it's basically up to the user to pick which one of these you think is best. But obviously, if you have a plume that's at, say, 11 kilometers, there's no real good one out of these. So how do we get around this? So in order to understand what altitude our plume is at, there are several methods to do this. The way that we do it here is using what's called PlumeTraj. And PlumeTraj is a sort of a software toolkit that has been developed at the University of Manchester for several years now. And this uses back trajectory analysis using global wind fields to trace each pixel back to the volcano. And we do this basically taking advantage of wind shear in the atmosphere. And this is basically the fact that at different altitudes in the atmosphere, you will be encountering different wind speeds, but also different directions that wind is blowing. The wind doesn't all blow in the same direction at all altitudes. That means if you start at a pixel, say here in the plume, and you launch all these trajectories at different altitudes, these will take very different paths throughout the atmosphere. And the trajectory that's launched at the correct altitude, so the altitude at which the gas is actually at, will be the one that goes back to the volcano. So by analysing how closely all these trajectories pass to our volcano, it allows us to know what was the true altitude of the gas at the time of measurement. So this gives us our plume altitude, which allows us to correct for this VCD by interpolating the correct air mass factor. But it also gives us our injection altitude and our injection time. So we get sort of all three in one fell swoop, as it were. And using all this information, we can then reconstruct our emission rates, which is what we really want at the end of the day. So without further ado, I'd like to look at some of these case studies that I mentioned before. So the first one we're going to be looking at is the eruption of La Soufrière, which took place in St. Vincent and the Grenadines. So a bit of background and motivation behind looking at this volcano in particular. La Soufrière has got this really long eruptive history with at least 6 eruptions in the last 1,000 years and more before that. Now, these aren't all explosive like the one in 2021 was. There's a mix of effusive dome building and also explosive eruptions. And sometimes you have explosions and dome building in the same sort of eruption sequence. Indeed, before this eruption, the previous one was in 1979, and that ended with a dome building phase, and that dome was existing at the start of the activity here. And some of these eruptions are deadly. They've been very dangerous. The worst one recorded was in 1902, which claimed over 1,500 lives. But there are previous ones before we had sort of better records that may have killed more people, sadly. So it's hard to know with those ones, though, but they are certainly a very dangerous volcano due to the sort of explosive nature of its eruptions. So this eruption, I say it's a 2021 eruption, it actually began in 2020. It just in the very end of December with a sort of effusive dome building. So here on the right, you can see a top-down image of the existing dome here in the sort of browny green color, and the new dome sort of grew to the side of it in a sort of weird beam shape. You can see here the colored outlines show the expansion of the dome with time. Now, the growth of this dome was roughly constant, growing to the side of it for most of this period, and it gave off very, very little sulfur dioxide. So they were just about managed to detect it using an in-plume sensor, so where you're actually getting up and close and personal with the plume. But it wasn't possible by, I would say, mobile DORIS here. That's a remote technique from the ground, and it also wasn't possible to detect any gas from space. Now, it's kind of changed in April 2021 when activity really picked up on the 8th of April. So this graph on the right here is taking data from Douala et al., who used SAR data, that's synthetic aperture radar data from different satellites, as you can see on here, to reconstruct the volume of the dome with time. You can see the sort of linear growth. So right before where you see the sudden uptick in the growth rate. And this was coincident with observations at the summit of more degassing coming off. There wasn't too many measurements of the actual gas, but it was giving off a lot more sort of steam. And we actually did detect SO2 for the first time remotely, both from the ground and from space. All of these sort of signals combined meant that the alert level was raised and evacuation order was issued, which was just in time because the next day, on the 9th of April, it went explosive. So these are just some of the pictures of some of these explosions that took place on this. We had an initial explosion on the 9th of April. It was followed by about a 4-hour pause, and then it went into a phase of basically continuously exploding and then they slowly sort of spaced out with time until the last explosion was on the 22nd of April. And this is just showing you here now that the time sequence of these. So we have our initial explosion here. I should say, sorry, the blue line here is using the relative seismic amplitude. So it's just a measurement of the seismic energy that's being given off at the time. And the orange vertical lines are timings of explosions that have been picked out by a paper by Sparks et al. And you can see here we have this initial explosion, a bit of a gap, and then this continuous phase, and then they sort of spread themselves out a little bit with the time difference in between each getting sort of longer as you go through. So what did Tropomi see? So this is a bit of an animation here. You can see some other volcanoes giving off a bit of gas, but it's dominated by this eruption that wraps itself around the globe very, very quickly. I should play that again. And one thing you can see is a lot of these gas actually got wrapped around and stuck around or returned to the volcano after a couple of days. And this really made it quite complicated for our analysis. So we decided we'd focus on just the first few days of the eruption to understand what was driving that initial explosion. So I'm going to be showing results from the 8th, 9th, 10th, and 11th of April. So the day before the eruption and then the first 3 days of explosive activity. So using plume triage, we were able to correct our satellite data to get the right plume altitude and also the plume agent injection altitude. And I'm also showing here what's called the UVAI, or UV aerosol index, which is an indication of ash in the plume. So positive values of the UVAI, or in this case, on this plot here, they'll be blue, will signify that there is ash there. It's not a perfect, it's a good sort of qualitative flag. So on these plots, I'm showing here the corrected BCD value on the left, the plumage on the center left, and the altitude on the center right. And note as we go through the scales on these will change quite dramatically as we get more and more gas. So the first one on the 8th of October, on the 8th of April, sorry, we were able to measure this precursory plume. It's quite small, but we were able to detect it, and we got some pretty good results from it. This was then followed by this initial explosion on the 9th of April, which formed this sort of beautiful hook-shaped plume. Much higher altitudes, this went up to 15 kilometers, and it was all injected basically at the same time. Oh, sorry, I've got the mirror. Much higher altitude, it went to about 15 kilometers, and it was all injected pretty much at the same time, actually. And there's evidence for a little bit of ash in the plume here, you can see. Then on the 10th and the 11th, consecutively, we saw this much larger plume. So we're going here from 20 to 100 to 500 kilometers scale, or even 700. You can also see that the BCD values here are much greater. And notice that this is also a log scale, so we're getting much more SO2 in this sort of main phase of the plume than we saw either in the precursory or in the initial explosion. But these are still being emitted at about 15 kilometers. The other thing to point out is this presence of this very ash-rich core nearer to the vent that we can see. I'll come back to that. So these are just the sort of reconstructed maps, but what can we actually do to look at the actual SO2 that was coming out of the volcano at the time? So using our injection altitude and time, we can reconstruct what we call our emission intensity. This is what we're showing on the top plot here. So this has got altitude on the y-axis and time on the x-axis. It's basically the darker the color on these plots, the more SO2 was coming out at that time and at that altitude. So it allows us to look at both the time variation and how the altitude of the emissions was changing. We're also showing just the SO2 emission rate. So it's basically summing across all altitudes what was the total amount of SO2 that's coming out. And on the bottom here, we're just showing this RSAM plot again, just for a comparison with timings and stuff. So another thing to note on these plots, we've got this sort of grey dashed line. This is the satellite overpass time. So we obviously don't have any measurements after that time because we only sense up to that time. And we can see that our sort of emission rates, although we do have very large error bars on these, they are in rough agreement with the ground-based traverse measurements that were done on the 8th of April. So that gives us pretty good confidence that we're doing a good job here. And then onto the initial explosion, you can see, as I mentioned before, it's this sort of very discrete pulse of SO2 that was injected at about 15 kilometers. And you can see it's coincident with a spike in RSAM. Our SO2 emission does have quite a slightly longer duration. It's not 100% clear whether it was actually being emitted over that longer time period or whether that's just due to spreading, in fact, of several factors. So we don't actually measure the emission time at the vent. We are measuring the emission time once it's injected into the free atmosphere. So it will take a finite time to leave the vent and reach 15 kilometers. And during that time, things will get mixed up. It's a very turbulent situation. So that's why you can sometimes get this sort of time spreading. Whereas the RSAM value will be what's happening like at that precise time. So that might be one reason why we have a more spread out SO2 plume compared to the RSAM peak. And then continuing on, see very strong emission still up at very high altitude, so still at about 15 kilometers, maybe slowly decreasing it as we go over time. But we're having really quite shockingly large SO2 emission rates. So these are looking at about 5,000 kilograms a second. Our initial explosion was about 300, and here we had 1. So it was really kicking out quite a lot of SO2. One thing to point out here is that we do see sort of systematic drops in the SO2 emission rate as we get closer to the overpass time. This is likely due to the presence of volcanic ash just basically blocking all the light, so we can't sense the SO2 that's in those parts of the flue. So it's very interesting, but what does this actually tell us about what was going on in this initial phase of the eruption? Well, we can also compare our SO2 emission rates with the total mass that was being erupted at the time. So this was compiled by Sparks et al. Used this RSAM data to estimate the total sort of mass flow rate that was coming out of the volcano for each of these explosions. So by taking the ratio of our SO2 emission and the sort of total mass emission, we can figure out how much sulfur was actually in the magma to begin with. So we did this for 3 windows, one covering the initial explosion, one covering the data that's available on the 10th of April, up until the point where we can see the sort of impact of ash, and then another one on the 11th of April. So we can get our sort of total SO2 mass for those windows. You can get a total erupted mass for those windows, and using the ratio of those, we can figure out a sulfur content. And what you can see here is that this initial explosion was really quite sulfur poor compared to the later activity. And this makes sense when you look at the original plots where we saw that the vertical column densities of sulfur in the initial explosion were much lower than later on, even though it reached the same sort of altitude, which wouldn't necessarily be what you expected. And this suggests that the initial explosion was very, very poor in sulfur. So what does this tell us about the eruption mechanism? Well, we sort of put together this sort of idea of the process. So we're suggesting that we started off with this sort of basically a plug of degassed magma from the previous 1979 eruption. There was already this 1979 lava dome at the top, and perhaps the conduit was filled with the old magma from that, and that had already lost all of its SO2 from degassing over the years. Now we get an ascent of this fresh magma, which was driving this main eruption, and this forces this old magma out, and it forms the old dome to the side. So although it forms the new dome to the side of the old dome. So although this dome was being built throughout this eruption, it was actually from the magma that supplied the previous eruption that had already lost all its SO2, hence why we couldn't measure any SO2 coming off this new dome. Now, as that old magma runs out, basically the friction that's holding it in place sort of drops off very, very rapidly as you run out. We start seeing SO2 coming out as this fresh magma is reaching closer to the surface, and we see this sort of sharp uptick in the extrusion rate of the lava, which probably just leads to some runaway reaction, where we have this initial explosion, which then clears the conduit, and then allows clearing the way for the main phase of the eruption of the sort of the fresh undegassed magma after about 4 hours later. So to sort of wrap up for Lassifray, by combining dropome imagery with Bloomfrad, we were able to reconstruct SO2 emissions throughout throughout this initial phase of the eruption. With this, we can detect this precursory degassing, which is an important sort of monitoring signal. And we also infer that the initial explosion itself was sulfur poor compared to the rest of the eruption. So all this is suggesting that the lava dome formed was formed from degassed magma from the previous eruption, which was forced out by this ascent of fresh magma, which then drove the main phase of the eruption. So on to eruption 2. The eruption of Fagradalsfjall was very different from that of Lassifray. I will start by having a little bit of background. So Fagradalsfjall actually erupted a little bit before the one that Lassifray, or it began its eruption on the 19th of March, again in 2021. And this ended about 800 years worth of quiescence on the Reykjanes Peninsula in Iceland. So this is this peninsula that's being highlighted in red here. You can see the event location here in green. Now, by looking at previous eruption on this peninsula, eruptive periods typically last about 200 to 400 years, and typically have about 800 years between each one. And so it looks like we've seen the start of a new eruptive period and indeed in 2022 and in 2023, in those 2 summers, we had eruptions from the same system, and we had an almost eruption, or there's sort of an ongoing crisis at the moment down in Grindavik from this volcanic system. So it's going to be, I think, a very key location for monitoring wise for the future, as this activity could be going on with regular eruptions for the next couple of 100 years. This is particularly important because Reykjanes itself is home to 70% of Iceland's population, as well as significant infrastructure for the entire country. So we have the airport, the main international airport in Keflavik here, as well as some of the main roads around the island, and also a geothermal plant in Grindavik. So there's a lot of very important infrastructure in this area, so it's important that we can properly monitor these eruptions. So we'll just be looking at the 2021 eruption. To give an overview of what was going on during this, we have sort of several phases. We have phase 1 to 5. Phase 5 is also sometimes referred to as phase 4B. So just if you see 5 and 4B are interchangeable in any of the plots that I show you. But we start the sort of first 2 phases. First month or so was quite weak activity, so it was multiple vents were sort of formed over time along this sort of fissure eruption. This consolidated into one main vent, and it had very strong activity starting in phase 3. And so this was characterized by sort of lava fountaining with a periodicity of 10 to 15 minutes or so, with quite strong lava fusion and gas emissions as well. Phase 4 was slightly different, where we switched to this more periodic phase, where we had about 12 hours of eruption activity, and then 12 hours off, and then 12 hours on, 12 hours off, with very little lava or gas emissions in the off phases. We then had about a week-long pause in activity, which was then followed in the end by a final low-intensity short period of activity before the eruption ended on the 19th of September. So again, what did Tropomi see? Well, we saw for the 185 days of the eruption, we were able to detect plumes on 85% of these. The days in which we weren't able to detect plumes were predominantly in the pause towards the end of the eruption, or in the more pulsating phase where we have the on-off period. And you should be able to see that as we sort of transition into that phase here. You can see we have plumes that appear, and then they're gone the next day, and then they're here, and then they're gone the next day. So we have this sort of on-off fluctuation, and it just depends on whether we hit it at a time where it's been degassing or not. So straight into the results. Again, we're looking here at the sort of emission intensity, so how the emission strength was. This is on a daily basis now, and as a function of altitude. You see in phases 1 and 2, you see very little gas come out. It really kicks up in phase 3. And then we have these sort of 3 main periods of high intensity, one here, and one here in August. We can compare our injection altitudes with those measured from the ground, because they had webcams set up to measure sort of the plume top and plume bottom altitudes throughout this eruption. It was very well monitored by the Iceland Meteorological Office. And what you can see here is that the sort of plume top in white and plume bottom in black here are very nicely bracketing our plume sort of limits. There are a couple of outliers. You can see sort of very small spots at a very high altitude, which are typically due to wind errors, or small errors in our wind fields that we're using to drive our back trajectory analysis. If I'm being perfectly honest, I was quite surprised at how well this worked. When we first looked at the results, I was very happy, because we are using a global wind model, 0.25 degree accuracy, so that's about 25 kilometers at the equator, to look at very, very small plumes, very, very close to the ground, where these models don't necessarily work so well. And we were still getting really excellent agreement in the plume altitudes. So this gave us quite a lot of confidence that our model was working very well. So IMO also performing traverses of the emission rates whenever they could. So again, this is where you sort of drive a spectrometer underneath the plume to take a slice of the plume to measure the amount of S2 that's coming out. The agreement between these is slightly more variable. We see the best agreement is in the sort of beginning of phase 3 here, where we have these sort of very strong, steady emissions at higher altitudes as well, where the satellite is better able to see it. It's hard to say which of these two is the better. The ground base doesn't really seem to capture any variation in the emission rates going from the first 2 phases to phase 3. So yeah, it's very difficult to say like which of these two is right. One benefit of the satellite measurements is that we are getting measurements every single day. These traverse measurements are very labor intensive to do from the ground and require a lot of work in post-processing as well. So they're very complementary data sets anyway. And we also compared these with just the amount of lava that was being emitted. So this is being measured throughout the eruption by photometry, so by just like 3D reconstructions of the lava flows. And we can see that we tend to see higher emission rates relate to periods where we have higher lava effusion, which makes sense. You get more lava coming out, you get more SO2 coming out. Also showing on this graph here, the blue dots are showing the sort of percentage crowd fraction of the plume. That's one issue that we get from space, and one issue that we were particularly worried about in Iceland is that meteorological cloud can block the SO2 from the sensor, especially when the SO2 is at very low altitude as it is here. But we don't really see a clear correlation between high cloud cover and low emission rates. So we think that the cloud cover wasn't really a big issue, and it certainly wasn't driving these variations that we saw. We think these are real volcanic signals. And in a similar way that we compared our SO2 masses with our explosion masses for Massif-Ferré, we can do a very similar thing here using the sort of amount of lava that was emitted. So again, we can get the ratio of our SO2 emissions to the lava flow mass and reconstruct a sort of variable for sulfur content throughout the eruption. There was some published data as well here in green that was taken from melt inclusions those sort of first few weeks of the eruption. You can see that at the same time, our values are quite a lot lower. These two are kind of outliers, more due to sort of low emission rates rather than high SO2 fluxes. So, and I think that's reflected by these very large error bars. So we're certainly seeing much lower sulfur contents than they had from the melt inclusions. Not necessarily surprising, this is a very low altitude plume. There's a possibility that we're underestimating the SO2 emission rates because we are probably working at about the edge of the detectability for our satellite. However, if the trend is correct, even if our absolute measurement is slightly off, then this might show the sort of, as with Massif-Ferré, the initial eruption was driven by a more regassed magma, perhaps that had been, a previous failed eruption, and then transitioned as we kick up in our SO2 emission rates. It's driven by the sort of more volatile rich magma, which again would make sense in terms of the activity that we saw at the surface. Now I'd be very keen once more data comes out from the melt inclusions throughout the entire eruption, because it was sampled throughout the entire eruption. I'd be very keen to see if they saw a similar pattern as well. So we're sort of waiting on that data to come out. So to recap for Fagarazo, we're able to reconstruct SO2 emissions throughout the entire eruption, finding really good agreement with the injection altitudes that we saw from the ground. And this is also very important in terms of local health hazards, because this gas is being permeated in the local area, and forecasting where that gas will go on any given day is very dependent on the altitude at which it's being emitted. So if we can get that information from satellites, that could help with that sort of hazard forecast each day. We showed that this is possible from space even for this very effusive low altitude eruption and high latitude eruption as well, where you have less UV light. And it's sort of opening doors for sort of wider eruption monitoring from space that we can do using droponi. And finally, we tried using this data to probe magnetic processes. This isn't quite conclusive, and we're waiting on updated geochemical data to compare to see how good our trend is. So eruption 343 is the eruption of Tacogate, which is the part of the Cumbre Vieja volcanic system on the island of La Palma in the Canary Islands in Spain. Very protracted sort of zooming in. So to give you a bit of an overview of this eruption, this is the island of La Palma here, situated in the Canaries archipelago. This entire sort of spine down the sort of southern half of the island is Cumbre Vieja, and you can see here the site of the 2021 eruption here. La Palma is quite an important island in terms of Canaries and eruption and volcanology in general, as it's the site of over half of all historical eruptions on the archipelago. So this is by far away the most active source at the moment. The eruption itself lasted from the 19th of September, which is coincidentally the day that the Fagaratsfjall eruption ended, pure chance, until the 13th of December. Thankfully, the eruption began in an unpopulated area, but lava flows did then flow down the flank of the volcano and inundate a town, and did destroy almost 3,000 buildings and required almost around 8,000 people to be evacuated. So this had a very, very strong social impact on the island of La Palma, and work is still ongoing to try and recover what was lost and rebuild the infrastructure in the island. It also severed, there was a main road joining north to south on this side of the island, meaning that a lot of people who had before a 10-minute commute to cross here then had to travel all the way around the island. So it was really disruptive, and obviously very costly to a lot of people for disruption it caused. So again, a very key one to monitor the ongoing eruption as it was taking place. So again, Tropomi captured the Esse plumes from this really nicely. The plumes were really quite complex, sort of being ripped up by the ambient wind fields and spread out in lots of different directions, and dispersed over a very, very wide spatial extent, extending for hundreds of kilometers. And we were able to see Esse emissions that were older than 24 hours basically every day. So they were very persistent in the atmosphere as well. We were able to detect Esse on every day of the eruption as well. So it was a very continuous flow of gas coming out. Now, as we did for the Isen case, we were able to compare our plume altitudes with those taken from visible webcams again. So this is, here it's just showing the plume top altitudes. You can see again the plume altitudes from the cameras are again bracketing the top end of our emissions very nicely. So again, this is a nice sort of demonstration of how well plume trajet is getting this injection altitudes back. They're looking at actually how much gas was coming out on each day. So here we're showing the daily mean Esse2. Change of units here, so the previous two were in kilograms per second. We're now looking in kilotons per day. If we were to convert 80 kilotons a day to kilograms per second, it would be about 1,000. So it's an order of magnitude more Esse2 coming out of this than there was from Fagaratsfjall, and maybe 5 times less than was being erupted for Lasufro, but this was going on for several months. So now the eruption actually began after the overpass on the first day of the eruption. So we get most of the emissions measured technically on the second day. So that's this sort of high peak. There's a very strong start to the eruption, settled down a little bit in this sort of linear ramp-up phase before peaking on the 29th of September. We do see this one day on the 27th of September, that's very, very low, and that is coinciding with a 10-hour pause in activity that took place. And then after this peak, the emissions sort of decay with time until the end of the eruption in December here. So on the bottom plot here, I'm also showing the cumulative emissions, so how much total had been emitted over time. And we see that after this sort of peak and the decay away, we see this very nice sort of exponential curve. This guy was thinking, like, if we knew this, if we had this data at the time during the eruption, would we have been able to forecast this curve? Because it's very well behaved. This is what we tried. So in these plots, the grey line here is showing the total cumulative curve that I showed in the previous plot. The black line here is imagining we had data up until this day, or the day that's printed at the top. And the orange is an exponential decay fit, and then projected forward in time to see how well we can do. And we basically step forward time to see at different stages of the eruption how well could we forecast it. first few weeks, it's just shooting off linearly, so there's no sensible eruption end time. But as soon as we see this curve, you can see that our projections actually match very nicely what we end up measuring. And the more data we collect, obviously, the more we can zoom in on the precise timing. If we look at the decay rates that we fit, so the tau value here, you can see this is very consistent at about 25 days, again, zooming in terms of the error on that fit. We can also look at what the final emission rate was compared to the sort of peak emission rate. And again, this is very consistently at about 5%. So what it says is that once the SO2 emission had dropped to 5% of the peak rate, the volcano was no longer able to support the eruption from the lowered flow of magma to the surface, and so was able to cease. And we can ask ourselves, do other volcanoes show this very nice trend? And there's some evidence here. So there's a couple, one from Wolf Volcano and the one from Kilauea. There's just a couple of samples I very, very quickly looked at, and you can see again sort of sharp increase and then a decay away from both of these over very different timescales. But so I think this isn't a isolated case. So this opens the door. Can we use this to look at to forecast the evolution of eruptions in the future? So to recap on this one, using tropomian plume charge, we can provide sort of 24-hour monitoring of SO2 emissions throughout the entire eruption. We found this sort of very steady exponential decrease in the emission rate, or the sort of curve in the cumulative emission. And we showed that it would have been possible to forecast the evolution of the eruption quite accurately in near real time during the actual eruption. So if I have piqued anyone's interest, there's some more extra reading you can do. We have a paper on the St. Vincent work that we did in the Geological Society Special Publications. If you're interested in Iceland, we have a paper in EPSL as well. And if you're interested in La Palma, keep your ears open. I submitted this yesterday, so hopefully it will be available soon for your reading. And sort of final take-home points, I'll leave this on. So for La Soufrière, we're able to quantify precursory degassing, very important for volcanic monitoring, but also we're able to probe quite deeply the eruption processes driving that initial phase. For Iceland, we showed that we can monitor even very weak effusive eruptions using the same toolkit that we use for this explosive eruption from La Soufrière, and it's very clearly able to identify changes in the eruption star from space. And then finally, for La Palma, we were able to forecast the evolution of the eruption from quite early on using the satellite derived SO2 emissions, which really sort of opens the door for future volcano monitoring. That's everything. Thank you very much.
Thanks, Ben. That was a really interesting talk. We now have some time for questions, so please put them in the Q&A. We don't have any yet, but I've got a couple to start. So obviously, most of your work is focused on SO2, but you showed some of the UV index for aerosol for La Soufrière, and I was just wondering how much does ash affect the UV retrievals of SO2, and how is that then affecting your plume charge results?
Yeah, that's a good question. It's hard to say sort of quantitatively, especially for the UV aerosol index. It's a very qualitative flag, so it doesn't necessarily mean a higher value is more ash necessarily. So it's hard to sort of say for definite what impact we're having. So we couldn't put a number on the underestimate that we're getting because of this. But we do see quite systematically that sort of sharp drop off when we do have ash in the plume. So I think it's quite important to remember to consider that. We actually saw a very similar thing in La Palma, very, very close to the volcano. It wasn't as much ash coming out, but there was still some. Very, very close to the volcano. We saw a quite sharp drop off in terms of the emission rate. So when we're constructing our daily emissions, we actually look from 3 hours before the overpass to try and remove that error. It's just something you have to bear in mind. There's not a definitive answer, unfortunately. It's quite difficult to correct this, basically because ash just blocks all the light, so you have very little information.
Have you tried retrieving or running plume charge for ash?
It's been discussed a few times. The problem we have is the fact that ash settles. So as it sort of drops slowly throughout the atmosphere as it drifts downwind. And having talked to people that know a lot more about these dispersal codes than I do, it's very hard to run deposition backwards in time. So if you're projecting the sort of dispersal of ash forwards in time, it's very easy. You have to assume the particle size distribution and different qualities of the ash, but you can predict how it will settle with time and then what different winds will take it in different ways. But the models are not currently set up to do that backwards. But it is something we'd like to look at in the future. Maybe for fine ash it would be okay, and there isn't too much settling, so it could work. But
that would be really interesting. We have a question from Anu Didier, who asks, does Tropomi retrieve SO2 equally well over bright land surfaces such as desert or ice?
Yeah, no, that is a good point. Yeah, it does certainly struggle. In the calculation of the AMF, there is a surface albedo term which does try to take this into account, but it is season independent. So obviously, where you have areas that have ice in the winter but not in the summer, you can introduce errors from that. There was a paper recently by a team in Japan. I forget the name of the first author, but they were looking at one of the emissions from a volcano on the North Island, and I think they do see a seasonality which they attribute to seasonal ice cover around there. Fortunately, most of the ones we were looking at were over the ocean, where it's all sort of equal. But yeah.
Great. Next question is from Thomas Wilkes, who says, "Thanks, Ben. Super interesting. Are there ever times where plume trash doesn't track a pixel back near the summit? And if so, how do you deal with this? And then following on from that, do you have any cutoff distance beyond which pixels are ignored if they aren't within X kilometers from the event?"
Yeah, I mean, there's several reasons why a certain pixel won't be able to be returned. One can be if the wind field isn't accurate. So, there's a lot of vortices or turbulence in the atmosphere that can cause these wind models to not accurately characterize the actual motion of the wind in the atmosphere. In those cases, you can get wrong results, so the plume won't return to the volcano. We also struggle with umbrella clouds. So if you have a particularly strong eruption where the plume rises and then spreads out before then drifting downwind, obviously this global wind model doesn't know there's a volcano there. It doesn't spread the plume out in an umbrella cloud before it drifts downwind. So we do try to take that into account with a certain cutoff distance. That is a user-defined term within the code. So typically, the larger the eruption, we tend to take values that are further away from the volcano. But that is a variable term. Typically, we use a cutoff of about 50 kilometers. So anything further than that, we don't take. But for larger ones, we can go up to 100 or even more to try and take into account that umbrella effect.
Great. So our next question is from Fathia Latviananda. Sorry if I'm pronouncing that incorrectly. Who says, "Hi Ben, thank you for an insightful presentation. I am curious about SO2 emissions, especially in various cases of eruption style. There are several cases of phreatic eruptions since it is a rich gas eruption event. Please correct me if I'm wrong. Is there any noticeable signature that can be used to forecast this eruption or style?"
Yeah, okay, so phreatic eruptions, I think, were typically driven primarily by water. So that can be water integrating either from like groundwater or seawater integrating into the magmatic system, and then that sort of flash turns to steam, and that sort of creates this explosion. So you don't tend to see many precursor signals at all before phreatic activity, be it degassing or otherwise. I think gas emissions are quite tricky when it comes to pre-eruption signals. We saw one in the case of La Soufrière, but it's actually pretty rare to see gas emissions before activity. So the primary precursory signals you'll get are earthquakes and deformation. So as the magma's making its way to the surface, it'll buckle the ground and obviously it'll crack the earth on its way in. So typically those are more useful for, I guess, forecasting or identifying precursors for eruptions that are going to take place. There are volcanoes that are passively emitting SO2 all the time, such as like on Etna in Italy. In those cases, we sometimes see a drop in the SO2 before a larger eruption. So those are probably more likely cases where we'll be able to use this information from a more sort of like routine monitoring perspective to try and forecast, or at least raise the potential of changes in activity like that. I hope that answers that question.
Okay, our next question is from Ibrahim Barry, who says, given that relatively magmas at depth are SO2 poor, don't you think that by doing similar studies on CO2 as well will give you a better grip on the degassing processes of volcanoes, and by doing so accurately predict or constrain their eruptive processes?
I would love CO2 emission data for volcanoes. We were talking about this before the seminar, in fact. The tricky thing with CO2 is that it's very difficult to measure, basically because you're trying to measure a relatively small variation in the CO2 signal over a much larger atmospheric column. So we have a lot of CO2 in our atmosphere. Trying to measure the volcanic signal on top of that is very tricky. The reason we tend to use SO2 as the primary one is because there is no SO2 in the atmosphere. So currently, the current satellite technology we have at the moment is not able to detect CO2 from volcanoes. There have been 1 or 2 studies that say that they have. It's a bit contentious as to whether those were actual measurements or chances. But there are more instruments coming up in the future that will be more sensitive and therefore could potentially detect volcanic CO2 over that. And that would be a complete game changer. So yeah, I completely agree. CO2 degassing signals would be a much stronger signal to use for this sort of stuff.
Great. Our next question is from Charles Forrester, who says, thanks for your presentation. What source do you use for your wind modelling?
I'm not exactly sure what you mean by source. If you mean the original meteorological data, we use the global forecast system 0.25 degree data from NOAA. And we use the high split model to run that through. We also use actually the UK Met Office's name model using their unified model data as well. But all of this data was using high split with the GFS data, but we do have the option to run with name as well.
Okay. Quick question from me. So you've obviously been primarily working with COMET. Do you have any plans to look at some other instruments? There's a lot of new satellites being launched in the next few years.
Yeah. I mean, any sort of imaging satellite that has these sort of daily images would work for SO2. We've just set up our workflow to work with COMET mainly, but there's absolutely no reason why we couldn't adapt the algorithm to work with any satellite sensor or any gas. Actually, we've also been doing some work in a similar sort of batch trajectory analysis of wildfire plumes of CO and NO2 using a similar sort of methodology. It would probably be this batch trajectory analysis might be less well suited to geostationary data when you're getting an image every 15 minutes, because our analysis time is not huge, but we might not be able to keep up with getting an image every 15 minutes. We can cope with daily though. So yeah, we would probably have to adapt our algorithm to look at the geostationary stuff, but more power sensors. That's correct.
Okay, thank you. So that seems to be it for questions. So I think we'll finish there. So thank you again, Ben, for a really great talk and for answering the questions. I want to remind everyone about the next COMET Plus webinar. That's on the 10th of January, and it's going to be given by Esse, also you can access some of the previous COMET webinars on YouTube. So thank you all for coming and for your questions, and thanks again to Ben for the great presentation.
Thank you very much for organising, and thanks for coming.